Today I want to talk about how to implement the tabulated equation of state and the neutrino leakage scheme into a code called HARM3D, which is a GRMHD code, and about the TCAN collaboration. So this is to study neutrino cold accretion disks. And the main purpose of the whole collaboration, which I'll talk about later, is to study the post-merger of two binary neutron stars and the subsequent accretion disk. So first, let me explain why do we want to study this. And of course, as everyone knows, we have found the first gravitational wave coming from a binary neutron star merger. And also there was an associated electromagnetic counterpart. So let me explain what happened. First of all, we had two neutron stars orbiting around each other. As they orbit around each other, they're going to radiate gravitational waves, which carry both energy and angular momentum. They're going to get closer, and they're going to, at some point, become dynamically unstable, merge, and they're going to form these spiral tails as mass is ejected from the outer Lagrangian points. Now, as Luciano already mentioned in his really cool talk, this merger is going to result in a hot, rapidly rotating and differentially rotating hypermassive neutron star that's going to be surrounded by an accretion disk. Now, depending on the mass of the remnant, the hypermassive neutron star can or will not collapse into a black hole. So in the case of GW17817 in particular, we will argue that the remnant is believed to have been a collapse to a black hole, but not a prompt one. So what happens? First of all, as the binary merges, there are several options for the resulting object depending on the final mass of the merger. So we have a first threshold mass. So if the mass of the remnant is larger than the mass at which all gravitating objects collapse, then it will just promptly collapse into a black hole. If it is less than this maximum mass, the result is going to be a hypermassive neutron star that's going to be surrounded by an accretion disk. Now, in particular, we know that this is not the case for GW17817 because the mass of the remnant is less than the maximum allowed mass. So prompt collapse has already been ruled out. Now, as the merger is cooled, what's going to happen is that this differential rotation is going to go into uniform rotation. So there we're going to have a different threshold mass. Now, if the mass of GW17817 is larger than this threshold mass, then again, it's just going to collapse to a black hole surrounded by an accretion disk. On the other hand, if it's less than the threshold mass, it's just going to become a supermassive neutron star or magnetar, and it's going to be stable and long-lived. Now, in both cases, we can expect a relativistic jet to happen. In both cases, it'll be from a different type of central engine. In this case in particular, it would come from the spin down of the magnetar. But again, from 17817, we have reason to believe, just due to some energetic arguments, that this is the case. So we know that GW17817 comes from a delayed collapse to a black hole. And as Luciano mentioned, the collapse should have been delayed for like around a second, more or less. So it actually was quite long. Now, as I mentioned before, we have studied GW17817 all over the electromagnetic spectrum, which is incredibly interesting. So the non-thermal emission in particular is really cool. It's really cool. So here what I'm plotting are the X-rays and the radio from this event. This is highly uncharacteristic of normal gamma ray bursts, which are expected when we have the merger of two binary neutron stars. This non-thermal emission should come from synchrotron emission from the relativistic jet as it interacts with the ambient medium. Usually you would see something that just decreases, and it's kind of like a broken power law. But in GW17817, we saw kind of like this rise and then this decay. Now we know that this could have just been due to the fact that we probably seen everything. We saw the GRB off axis. So instead of looking at the jet directly, which is what we normally would have seen, we looked at it at a different observed angle. So this naturally explains the emission, and particularly this comes from a structured jet, which I'm not going to go into a lot of detail, but it's also very interesting. So this is all that I'm going to talk about the non-thermal emission, but please feel free to ask me a little bit about jets because they are also very interesting. For the rest of the talk, I'm going to focus on the thermal emission of GW17817. So the kilonova, which is the thermal emission, was incredibly important because we actually saw the optical light first. We saw it first, and then we saw the X-rays, and then we saw the radio. So this was what allowed us to localize GW Sentinel 17 and then make it the most observed object ever. So the kilonova is quite important. And here is just like the discovery picture, which is always really cool to show, because here you see nothing. And then on August 17 of 2017, here you see clearly a transient. Now, this emission is unlike anything we've ever seen before. So at first, this emission was extremely blue, but after a couple of days, it became very, very red. Now, people have explained this emission by the radioactive decay of our process elements. So in these really high densities and very high temperatures, we also have very neutron-rich material. We expect that the neutron captures occur more frequently than the beta decay, which is the R process. So in this plot, what I'm showing is the number of protons and the number of neutrons. In the case of the R process, neutron capture, which is in this direction, occurs more than the beta decay, which occurs in this direction. So we're going to form elements around this part right here. So these are the stable nuclei, and normally this is what we see on Earth, but the R process has really, really high very neutron-rich material. So what's going to happen is that these R process elements are going to then decay into the stable elements, and by doing so, they're going to emit in the optical light. So this is what's going to happen. For example, this is the composition of the remnant, dynamical ejecta, and we can see that everything is going to start to form this very high neutron-rich material, and at some point it's going to decay, and as it decays, we're going to observe the light curve. So then the emission of the kilonova can be explained by the radioactive decay of fast-moving ejecta. Now we see two different components, and as David pointed out on yesterday, if I believe, we have two different components. We have the red component of the kilonova, and we have a blue component of the kilonova. The origins are still a little bit under debate, but what we actually know is that this red component should have been from lanthanide, from ejecta that has a lot of lanthanides, the forgotten part in the periodic table. So these lanthanides have very high opacity, so they're going to be red. Whereas this blue component is going to be also a very fast moving but lanthanide-free ejecta. So this means that this will have lower opacity. So both of these two components are the ones that are expected to explain the kilonova. So here I'm showing this really cool movie. This is the brightness, and this is just dates since merger. The dots are the real data, and the lines are just the model for these two components. So as you can see, this two component model fits the data pretty well. So it is fairly understood that this is probably coming from a two component model where you have a red kilonova and a blue kilonova. This is with lanthanides, and this does not have lanthanides. So what kind of outflows can form this ejecta? So there are a lot of them, and I think Davide went through the majority of them. And for the majority of the talk, I'm going to focus on this MHD stress-driven outflow. So if we have a black hole and an accretion disk, we will also have lots of magnetic fields just due to the initial configuration of the binary neutron stars. And from GRMHD simulations, we expect that magnetic torques are going to bring material from the disk to the black hole. And as material falls, there's going to be this very powerful outflow that's going to be accompanied by a relativistic jet. So here I'm showing this movie. This right here is the black hole. This is the accretion disk. And as material falls, you can see this accumulation of magnetic field. You can see this jet that is forming. And here you can actually see, so this is the mass accretion. This is the mass accretion rate. And this is the efficiency. So you very clearly see this very powerful outflow that's flowing from the accretion disk. And you also see a very powerful relativistic jet. So let's discuss the physics in the accretion disk and what kind of physics matters the most. So due to these very high densities and high temperatures, photons are going to be trapped everywhere in the flow. The outer regions of the disk are going to be composed of alpha particles. And as we go into inner regions of the disk, what's going to happen is that the density increases, the temperature increases. So those alpha particles are going to dissociate and become free nucleons. So this part in particular is going to release a lot of energy, and it's going to create this wind. And also it's going to thin the disk, because since photons are trapped, this disk is going to be very thick and radiatively inefficient. As we go into inner regions, what's going to happen is that the beta process right here, which is the charged beta process, is going to be ignited. So neutrinos are going to be created. As we know, neutrinos are going to then cool the material, because their cross-section is much, much lower than the photon's cross-section. So they're not going to interact with a lot of the matter. So they're going to just be released and cool the disk. So the disk is going to become thinner. Now, at some point, which is not the case in our conditions, if the mass accretion rate is high enough, the neutrinos could become trapped. But again, that's not going to happen in these kinds of accretion disks. We need a really high density and high temperature. But in general, we will have neutrinos, and we will have also a region which is opaque to neutrinos. So neutrinos will follow, in general, these reactions. The charged beta process, there's going to be electron-positron pair annihilation, and there's also going to be Plasmon decay. All of these three and other reactions are going to be the ones that create neutrinos. Now, what I wanted to notice is that, not surprising, the material that's coming from the neutron star is going to be extremely neutron-rich. Therefore, in this charged beta process, which, by the way, is the dominant process, this reaction is going to be the most dominant one, just due to the fact that we're going to have lots of neutron-rich material. Therefore, we're going to form a lot of antineutrinos. So more antineutrinos of the electron are going to be formed than the electron neutrinos. On the other hand, we have this absorption, which is our opacity source. And this reaction right here is going to be the most dominant one. Now, since this reaction is the one that has the neutrinos are actually going to be more opaque, and they're going to become opaque first. So let me just recapitulate, and let's see what we learned. So here what I'm showing is the mass accretion rate and the radius. So let's choose a radius and try to understand what happens. So in the outer regions, again, it's going to be composed of alpha particles. The photons are always going to be trapped. So in this part, the disk is going to be thick and radiatively inefficient. Then we're going to have dissociation from alpha particles to free nucleons, or recombination if we're going in the other way. And this is going to release energy. Then if we're going to inner regions, the beta processes are going to be ignited. So the disk is going to be cooled by neutrinos. At some point, the densities will be high enough so that we become opaque to neutrinos first, and then we become opaque to antineutrinos. So this is more or less what is going to happen in our disks. Of course, the neutrinos could also be trapped, but again, that is not the case. Now, in order to fully understand what happens in the disk and this MHD-driven outflows, we need numerical simulations that include general relativity, because we're talking about black holes right here. We also need MHD because all of this has really high magnetic fields, so we also need to have that into consideration. We also need a realistic equation of state that includes this recombination energy. And we need some kind of like transport, or some kind of like approximate transport, in order to consider the neutrinos and how they thicken and how they thin the disk. So we need all of that to understand this MHD-driven outflow. Now, why do we actually care about this? So again, as I've been telling you, this outflow at some point is going to become unbound and at very high speeds. It's going to then be the perfect place for nucleosynthesis of very heavy elements such as gold and platinum. Now, the main issue is that different neutrino treatments or different treatments in the simulation can lead to very different results in the final abundances of heavy elements and the final ejecta mass. In particular, for example, the electron fraction, which is the quantity that we most care about, is the one that's going to dictate the final nucleosynthesis. And the neutrinos are going to severely alter the electron fraction. So there is actually a lot of debate on whether lanthanides are created in this type of ejecta or not. So this is still uncertain. And we need to settle this debate because, again, as this material expands and cools, the elements will radioactively decay and will produce the kilonova. So here again, it's just the kilonova in GW170817. And the thing is that, of course, lanthanides have very high opacity. So if they are created, they will make the kilonova peak later and be redder. But if there are no lanthanides, then the kilonova is going to be bluer and it's going to peak earlier. So this is extremely important information for our observer friends because they need to know when to look and how to optimize their surveys. So we need to make better simulations that estimate these abundances. So I'm going to present here one of our simulations. This is of course not the only one, but it's the one that I participated in, so it's the one that I'll present. So I'll talk about how we added a tabulated equation of state and a neutrino leakage scheme, which is an approximate neutrino transport scheme, into HARM3D. Now this is a stepping stone and will allow for better neutrino treatment to be added, which is already on my to-do list. Now let me talk about HARM3D. Most likely, some of you have already heard about HARM, and most likely, at least I know that a lot of you have already used HARM. So HARM is a code that solves the GRMHD equations in a conservative way. It is extremely well tested. Lots of groups have been using HARM for years now. In particular, this version can handle arbitrary grids, like the one that's shown right here. And since it has kind of like a spherical grid, it has also much less distribution than a Cartesian grid. And this is all part of the TCAN collaboration. So here I'm going to spend a little bit more time. So this TCAN collaboration is a collaboration led by Manuela Campanelli, who's going to be talking, I think, on Thursday, but you can check the schedule. So the goal of this collaboration is to do the most realistic simulations as possible of a neutron star merger from the binary to some seconds after the merger. So this is a very ambitious project, and there are lots of interesting people working on that. So what's going to happen is that first, we're going to use Lorraine, which is a spectral code, as initial data to get the two binary neutron stars. So then those are going to be the initial conditions. Then they're going to be evolved in two different codes. One is Illinois GRMHD, and the other one is PRIX. So these two codes are Cartesian grid based, and they also can handle numerical relativity. So they have dynamical spacetimes. So these two codes are going to evolve the neutron star. So it is expected that the neutron stars are going to merge, then collapse into a black hole. And then the simulation will be interpolated into HARM3D, and we're going to be using that as our initial conditions. So in particular, I'm part of the team that will handle the HARM3D simulations. So I'm going to be doing the post-merger simulations. We're going to then run the simulation for a second in a very, very large grid, of course in 3D. And we're going to get the final abundances using Skynet, and then we're going to get the light curves. So the purpose is to do different cases. We're going to try to do a direct collapse, a delayed collapse, a longer delayed collapse, maybe a stable neutron star. And if you want more information, you can check out our website right here, which is compactbinaries.org. So yeah, if you have any questions, just feel free to ask me about this, but you can also check the website right here. So this is just some shameless publicity. Now, in particular, my part in this work was to add a tabulated equation of state into HARM and a treatment of neutrinos. So what I did was I added an interpolation of the equation of state from tabulated equations of state. So there are some equations of state tables from stellar collapse in particular, and now HARM3D is agnostic to those tables. So in particular, the equation of state comes in two main places. So I'm going to focus more on the conservative primitive variable solver, but you also need, of course, the equation of state to get the sound speed. So this in particular for codes that have GR, it's extremely important to understand what happens, to have a routine that can handle a good conservative to primitive solver. Because as you probably know, in GR, you have a set of equations that are coupled, and when you try to go from conserved variables to primitive variables, you have this system of equations that are coupled. And so it's really difficult to solve them. So you need to be very clever as to how you're solving them. So let me try to explain a little bit about the different methods that we're using to go from conserved variables to primitive variables. So the first routine that we have is the one that's already in HARM, which is a 2D method. So in this case, and I'm not going to go into lots of details, but we have two equations to solve, and we have two independent variables. So the idea is to use a Newton-Raphson method in order to solve these two equations, get the independent variables, and with the independent variables, you naturally get all the primitive variables. And right here, our conserved variables are, for example, this Q, this B, and other conserved variables. In particular, when we're talking about the equation of state comes in the calculation of the enthalpy right here. Well, this is kind of the enthalpy. This is similar to the enthalpy. And also, of course, the pressure. So we need to take all of this into account when doing the equation of state solver. I also added some other 2D methods. So this is a great method because this one is very similar to the 2D method, but it has safe guesses. So it's a more robust method. There's also, I added a dogleg method, which allows for a most robust convergence. And the nice thing is that you don't need to have an incredible initial guess in this case. These are kind of some trust region methods. So this also adds robustness because unfortunately the 2D method is, although it's really good, you will see that it's not the most robust. There's also the 3D method. So in this case, we actually have three equations and three independent variables, where again, the equation of state comes in the calculation of this enthalpy, the pressure, and the internal energy. We also have a Palenzuela routine, which is a 1D method in which you solve this one equation with one independent variable. So we added all of those routines. And what we did was to test the EOS tables. We created first some primitive variables just based on density and temperature. Then we perturbed them. We then transformed those to conserved variables. And we used our U2 methods to go from those conserved variables to the primitive variables and just check the relative error. So here what I'm plotting is the relative error. Each one of these squares represent one set of primitives that was tested. And these are all the different routines. Now, what I want you to notice is, first of all, the white dots right here represents primitive variables where we had non-convergence. So the 2D routines are quite, so the 3D routine is by far the most accurate. It's also the fastest one, but it is the least robust one. So it actually has the most white dots. The 2D routines are not as accurate as the 3D, but they are pretty accurate too. And they are actually also, they're more robust, but they're slower. Whereas the Palenzuela routine is the least accurate, but it's also the most robust one. So what we did is then we had the 3D routine be the primary routine. And then if it fails, it goes to the 2D routine. If it fails, it goes to the safe guess. If it fails, it goes to the dogleg. If it fails, it goes to the Palenzuela routine. So we're doing all of that. And we're actually now implementing another routine, which in theory will never fail, which is the Castown routine. So this is in progress, but it's almost done. So let me just say about some lessons that we learned when we did all of this. So, well, first of all, what we did is we did a torus, and we did a torus that is isentropic, and it has the enthalpy by Fishbone and Moncrief. What we found out is that in order to take into consideration the equation of state, the enthalpy from the tables can actually be less than 1. So what we needed to do is we needed to move the boundary of the Fishbone-Moncrief enthalpy to be, instead of 1, or when the enthalpy is 1, it should be where the enthalpy is equal to the minimum enthalpy of the tables. So that is a very important lesson that we learned about the equation of state. We also learned to be very careful about the atmospheric treatment because the atmospheres can collapse. So what we did for this particular part in the equation of state is we set the density to decreases of power law, and we also set the atmospheric density very, very low. So what this does is that it helps the atmospheric material, it slows how it falls down. So then the atmosphere doesn't collapse anymore. So again, as I already mentioned, we also need to add more robust U2 prim routines, which is in progress, because we still have failures, particularly near the black hole. So we still need to add more robustness with these types of routines, but this is already in progress. So then that already takes care of the tabulated equation of state side. Now let's go into how to take care of the neutrinos. So what I did was I added a leakage scheme. So this is again an approximate scheme. This is not as nice and fancy as all the other schemes that we've talked about this week, but this is a stepping stone. So this will be the first step, and then we'll just make it better and better. So the leakage scheme considers these three types of processes to make neutrinos. And we have absorption as our opacity source, and we also have scattering with free nucleons. In the leakage scheme, what happens is that you add the emission of neutrinos as source terms. So in here, this Q is the heating or cooling rate from the neutrinos, and this R is the absorption or emission rate. This Q and this R are analytically calculated. So we have this R effective, which I'll explain what these two things are. And it uses spectrally average quantities. So it's a gray scheme. What's nice about this leakage scheme is that we actually interpolate, we have an interpolation from the opaque region and the very thin region, or transparent region. So if the diffusion timescales is really large, so we're in the opaque region, then the rates just become normal diffusion rates. Whereas in the transparent regions, we calculate the opacities for each neutrino and antineutrino, and then we just have that the rates are each of the processes rates, and the same for the heating rate. So this is for the leakage scheme. Now let me go into how we calculated the optical depth. So the optical depth comes into play when we're calculating the diffusion timescale. And as you probably know, the optical depth is really difficult to calculate because you need to do some kind of ray tracing or other interesting methods. So what we did was, instead of using a global approach like the ray tracing, we're using a local approach, which is the one that's described in this paper, Nielsen et al. So let me explain what happens. Let's imagine that we have, for example, a sphere of material. This has a constant density inside the sphere and a constant density outside, constant temperature, constant everything inside, and constant everything outside. This sphere has a high optical depth and it's opaque, whereas the material outside is optically thin. So let's focus on a cell right here. What this process does is that it calculates the kappa ds to each of the neighbors, and then it minimizes. So this is, for example, kappa, and this right here is ds, just using general relativity and the metrics, but this is kappa ds. So it calculates the kappa ds to each of the neighbors, and it says, okay, so I'm in this cell right here. I calculate the kappa ds to each of the neighbors, and we minimize over the kappa ds. So we're basically telling the neutrino, this neighbor right here, for example, is the one that is the path of this resistance. So your path is going to start to go here. And then you do this iterative method. So, and then you tell the neutrino from this cell where else to go, by again minimizing this tau, which is the kappa ds to each of the neighbors, plus the kappa ds to the neighbors themselves. So what you're doing is basically tracing a path out for the neutrino by doing this iterative method, but it's a local calculation, which is really nice because you don't need to do all the communication between all the blocks or everything. You can do this very locally. So you're basically, again, tracing a path of this resistance. So let's again take the example of the sphere. What's really nice about this example is that we can analytically calculate the optical depth as a function of radius. And this is right here in pink. And what I'm showing...
Mind to take a question?
Yeah, sure.
I have a short question. So don't you need to solve the geodesics of the the neutrino?
So everything, I mean, I guess you can absorb everything into this term right here, right? It's like the metric term. So this is mainly saying the path to the path out, but everything that's in the metric, it's already been absorbed here. Does this make sense?
Yeah, it makes sense, but but the neutrino emission and absorption takes place along the trajectory, right? Neutrino absorption and emission takes place along the trajectory, right? No.
So we don't consider reabsorption. Is that, if that's what you're asking? We only, so the only place where the optical depth calculation comes in is in calculating this diffusion timescale. That's yeah, that's all that we do. We do not consider reabsorption. That is also on my to-do list. But yeah, this is not reabsorption. This is just to calculate the opacity and the diffusion timescale. So basically, it's just to calculate the effective rates.
Thank you.
You're welcome. So here I'm showing what one iteration of this minimization would do. So it would tell like if the neutrino is right here, for example, it would say like, oh, go here. But it doesn't calculate fully all the optical depths if we want to go more inside the sphere, let's say. So in order to do that, we need more iterations, because as we increase the number of iterations, we're basically tracing the path of the neutrino. And if we do more iterations, we're tracing it more and more and more until we reach a limit. So what I did was I implemented a convergence criterion that takes care of that and tries to minimize all the iterations, which actually, once you put the initial guess, well, I'll explain this, but what I'm showing right here is, again, this sphere. This dashed line represents the analytical optical depth. And the solid lines represent the optical depth from the simulations with our convergence criterion. Now, what we do is we do one initial guess at first. And in this initial guess, we take 20 times the maximum number of cells in all of the directions of iterations. So we're basically doing a very good initial guess. And after that, we do a convergence criterion. And after the initial guess, it only takes 1 or 2 or 3 iterations in order to converge, which is really nice at each time step. So this is actually not super expensive. Now, some tests for the leakage scheme, for example. So what we did was we evolved an isotropic, optically thin, constant density gas. And what's really nice about this is that the equations then reduce to these 2 equations right here, which can be solved semi-analytically. So what I'm showing...
Sorry to take another question, please.
Sure.
What are you iterating? I didn't quite understand.
I'm sorry?
Could you speak louder?
What are your iterations in the previous slide? I didn't quite understand what you think iterating.
I'm sorry, I'm still not hearing.
In the previous slide,
you
said you've got your guess and then you do a certain number of iterations. But I didn't understand what are these iterations? What are you iterating?
So yeah, sorry. So I'm iterating over this quantity right here. So when you calculate this, so what you do for this type of calculation is that you calculate first the kappa ds to each of the neighbors, and then you do you say tau, the new tau, let's say, is equal to the minimum of this kappa ds, and then you do it again. So now you assign the tau right here to be the minimum of kappa ds. And then you do again a different iteration, which is the minimum of that tau plus the kappa ds to each of the neighbors again. And then you kind of iterate. That makes sense. So you iterate on this minimum right here.
Okay, I got it. Thank you.
Well, and so we tested the leakage scheme with, again, this is just an optically thin constant density gas. And what I'm showing right here in the dashed lines is the semi-analytical solution. And in the solid lines is the result from our simulations. So this is just a test, and we did actually pretty well. So that's always nice to know. So with all this testing and so now we basically have an equation of state ready that can consider the tabulated equation of state. And we have this leakage scheme ready that considers in an approximate way the effect of neutrinos. So then let me show you, of course, like the results, which is the interesting part. So What we did was we simulated a magnetized torus with a realistic equation of state and neutrino cooling. So again, what we did is we set up a Fishbone-Moncrief torus that is isentropic. It has a mass of 0.03 solar masses. And this is simulating the post-merger torus. So here I'm going to show movies. This is very zoomed in, very near the torus. This is the electron fraction, and this is the density right here. So let me just put it, but I want you to notice that one of the things that you can notice right immediately is that the disk, even at very high times, it stays very neutron rich. So this confirms the self-regulating mechanism that has been found in the past. So the self-regulating mechanism is just that the MHD heating is balanced. Well, so the heating from the accretion is balanced with the cooling due to the neutrinos. And this makes this disk very neutron rich, which is really nice. So you have this source of neutron rich material always. And now another thing that I want you to notice, and let me replay it again, is this wind that's created right around here, which is the wind that comes from the alpha recombination, or alpha dissociation, or the recombination from nucleons to alpha particles. And I'll show you exactly where this transition happens in a different plot. Now I'm going to show you the same simulation, but this is really zoomed out. So I don't know if you can see it, but this little tiny dot right here is the torus right now. It might be better here, like this tiny torus. So, I mean, it'll be pretty obvious why I needed to zoom out, but I want you to notice two things. So first, I mean, you get this unbound ejecta, like it's going really, really fast, and it just goes out of the domain almost immediately. And also, again, you have this kind of like wind, which is just due to the alpha particles. So I'll let it run. This is a 3D simulation, by the way. So now let me just show you several quantities right here. So here I'm showing the thickness as a function of radius, or the h/r of the disk. And this is just averaged over some times. And this is the average mass accretion rate as a function of radius. And in pink right here, we have zero mass accretion. So here, negative mass accretion rate means that it's going outwards, whereas positive mass accretion rate, it means that it's going into the black hole. So immediately you can notice that there is this very clear transition right here of something that moves outwards and something that is moving inwards. So the neutrinos are actually acting in this region right here, whereas around 100 kilometers or so is where the alpha particles are dissociating and driving this wind. So all this material, all this wind material is just from the alpha recombination. And here where the neutrinos are acting. And you can clearly see the effect of neutrinos in this plot. So this again is a transition. So here is where the wind occurs. And it's basically it thickens the disk. And as you go inside, the neutrinos are cooling the disk and they're thinning the disk. Now notice, of course, it's not a super thin disk, like some 0.05 or something, it's 0.1, 0.2, but it's thinner than when we started with. So the neutrinos are doing a great job at thinning the disk. Now here I'm showing the neutrino luminosity and the mass accretion rate. Now, not surprisingly, the luminosity from the electron neutrinos and antineutrinos is way higher than the other ones. So this X means the neutrinos from the tauons and the muons. So I mean, not surprisingly, they're orders of magnitude lower. And also not surprisingly, but interestingly, is that they follow pretty much the mass accretion rate because the neutrinos are created due to this heating from the MHD stress, just come from all the material just coming into the black hole. So it heats up and the neutrinos are created. So all of that has already been published, which is really nice. And all of those were tests, including kind of this one. So this, although this already confirms some other results, it was also a test that we did. What we actually want to do, of course, is the future, which is a TCAN collaboration. So what I'm going to show right here is a movie, courtesy of Federico López Armengol. And let me put play. So in this movie, right here, we have the two neutron stars. So this is kind of what the collaboration wants to do. So this is 2 neutron stars in this code called Illinois GRMHD. Here you can notice that these are the grids. So this is it has adaptive mesh refinement. So these are the blocks, and this is a Cartesian grid. So in Illinois GRMHD, we put first the 2 neutron stars and then we evolve them. So I'll just evolve them. This is already with a realistic equation of state. You have the hypermassive neutron star right here, and you're going to start to see the collapse. It should be happening right about now. The collapse of a black hole, everything collapses into a black hole. And we're surrounded by this accretion that's right here. Now, I'm going to pause it right now. What the movie will show is then the handing off from Illinois GRMHD into HARM3D, which is something that's never been done before. And so this is the Illinois GRMHD results. And when the grid changes, this is the initial conditions into HARM3D. So as you probably saw, there was not a lot of change from the material in the torus, because I mean, it's as it should be. And then these initial conditions are going to be then evolved in HARM3D. The advantage that HARM3D has, again, over Illinois GRMHD is that we can handle extremely large grids. So actually the grid for the simulation is around, it's 72,000 gravitational radii, and it will allow for a second of simulation to fully follow all the outflow for a second, which is really interesting, and it cannot be done in those types of codes. And this is the same simulation, but just seen from a different angle. And again, everything is going to collapse into a black hole, and it's going to be handed off into HARM3D. So the simulation that you're looking at right now, in particular this one, is, as we speak, is running in Frontera with the leakage scheme and with a realistic equation of state. So stay tuned. So basically all of this is in progress, and it's literally like in Frontera right now. It's actually in the queue, not running, but it'll be running this week more. So as conclusions, we perform simulations on a magnetized torus and study the impact of neutrinos and recombination to alpha particles. And this is with the new code that we called HARM3D plus nuke, which is just HARM3D, but with tabulated equations of state and a neutrino leakage scheme. So we're ready to perform these types of simulations with the TCAN, and we're ready for the handoff, and we're actually doing that right now. So thank you very much. And if you have any questions, just let me know.
Thank you very much.